Okay, see?
Yep.
Okay, so then let's get started. So I tried to do it short because some of them are midnight. So first of all, I will introduce the diagram of the our HPC and quantum systems in the Rikan Jan HPC quantum project. So first in Kobe, so we have a supercomputer Fugaku, and we have a IBM superconducting machine. And next spring, so we will have a GPU cluster mainly for the quantum simulations. And so this is connected to the SciNet, which is a backbone network of the Japanese Academic Institute, University Research Institute. So and through this, so we have connected the University of Tokyo supercomputer, University of Osaka supercomputer, and RQ and the quantum strapped to your machine. So this is installed in the main campus of Riken, and Riken's superconductive quantum computer. So I will omit this. I will just introduce this slide and omit the detail of which one. So IBM Kobe is head of superconductor 156 qubit, and Quantum Playmate is a Quantum H1 Attractive machine of 12 qubit, and the Riken A is a superconducting machine of 64 qubit. It will be upgraded to 144. So I will omit the detail of them. So we are conducting two different projects. So one is a Riken's internal project, which connects supercomputer Fugaku and Riken's quantum computer. So the other one is involving several university and companies. And this is connect supercomputer Fugaku and several supercomputer universities and commercial quantum computer. So the purpose of this right-handed project is to enhance the early commercialization of quantum computers. So anyway, so before we start our project, we perform a proof of concept experiment to connect Fugaku and a quantum superconducting quantum computer through internet service and REST API. So at that time, so we just submit a very simple quantum circuit to quantum computer from supercomputer to confirm that we can submit quantum algorithm to quantum computer directly from supercomputer. So first we have kind of the submission parameter program, which is originally designed for the A with Python. So actually, so QReq is a REST interface for quantum computing developed by University of Osaka and Kuransis. So this is especially designed to make use of A's cloud service. So by using this, Fugaku submit quantum circuit to quantum computer. Another one is that we omit Python and move to C++. So we just directly use REST API by using the C++ libraries developed by Microsoft. And the right-hand one is an example of the using Python one, and the right-hand one is C++ one. So in this case, so we perform a simple step-by-step hybrid algorithm, which first automatic generates given quantum state of images, grayscale of images, and then we send it to quantum computer, and the result will be visualized in a PIN format in the supercomputers. And in this graph, so we just put the execution time of the to use a quantum computer, including the communication between supercomputer and quantum computers. So x-axis is a number of trial, ideal trial, and y-axis is the total execution time. And the first breakdown, the first navy field is polling and transpiled the quantum computer backend side. And the gray is circuit execution and post and pre-processing in control servers of quantum computers. The red one is only appears in the left-hand side is a Python communication library overhead. And the last one is other overhead. We cannot identify what is the reason. So, but anyway, we first thing is that the Python library induce large overhead. so especially in case of supercomputers. And the second observation is that polling time will be dominated. So in this case, in this case, there's not so many users rather than us. But if there are many users, it is obvious that these parts, these navy part will be grow and grow and grow. So that we consider to we design our quantum HPC based on the observation of the proof of concept experiment. So first, we found that the programming model cannot use in our supercomputer system. So that we need a coordinated scheduling with quantum computer and supercomputer. And we need execution of HPC program running multiple nodes. We have to avoid the waiting time of HPC program running on multiple nodes. And major programming environment, quantum computer program development, a Python-based framework. But actually, Python is not so effective to be combined with HPC program. So so that we try to move to C and C++. So then let me do this. So then we consider the quantum HPC program as a two-level programming model, workflow and task-based priorities. So in the workflow, the tasks this is considered that the fine-grained task of a job over the supercomputer or quantum computer. So we ask users to separate jobs of supercomputer and quantum computer as possible as. And then our workflow engines submit each of job in a certain order based on the dependency between job provided by user. So we expect three different jobs in the workflow. First is simple HPC, and simple quantum, and HPC quantum. The second level programming model of this level programming model is HPC quantum job. So this is a single job from the viewpoint of HPC, but some of kernel will be offloaded to quantum computer directly through remote procedure call. The single HPC quantum job may offload multiple kernels, and RPC is asynchronous mechanism, so we can do something during the while waiting the result of quantum computer. So the motivation of the first programming model is obvious that we try to avoid the waiting time in quantum computer and supercomputer. So users may separate quantum kernels and HPC kernels in their applications, define the order of their executions. So job scheduler in both computer may arrange jobs to maximize the throughput in the system. Of course, you have to await the result of the previous task, but this waiting time may not consume any computational resources. So originally, we consider the image of the scheduler written in the left-hand side. So start reserve HPC and quantum resources simultaneously. But if a program is shown like here, HPC, quantum, then we cannot avoid the idling time in one of them. So on the other hand, if we use a workflow manager and submit the job to the job scheduler, so during the so this kind of waiting time can be used to different users effectively. So this is the motivation of the first level. For the second level, even we ask our users to separate quantum HPC kernels carefully, but sometimes some of them are very tightly coupled, or each of the portion of task is very small. So in this case, the user may combine them in a single HPC job, and some of them will be offload directly from a supercomputer to quantum computers. So in this case, even in this case, if we allow several users to submit a job to quantum computers, so maybe this part must wait the result of the quantum computers, and sometimes because supercomputer consume a very large amount of energy, 20 to 30 megawatt per hour, it is not a good idea to make it idle. So to avoid this, so the request from a supercomputer is something special. So we allow it to plug in the other general quantum users, and it is always prioritize the first position. So we design, so this is diagram shows our execution environment. High priority execution requests from HPC are always in the first position of the scheduler. So to do it, we design and develop lightweighted schedulers. We call request schedulers. So first, there's a workflow engine, and it may submit something to HPC or Quantum. And some of the HPC jobs include quantum kernel offloading. And this quantum kernel offloading and a simple quantum job is called our lightweighted schedulers. And this identify that this is coming from the supercomputer, or this is just a simple quantum job. And if it is considered to come from the supercomputer, then it is put to the first position and run it immediately after something on the quantum computer is done. So this diagram shows the inside of our quantum schedulers. First, one client sends a broker module to the request. So broker module is in charge of the communication between client library and scheduler. And then it registers job to a database, and currently we use SQLite. And then this is also sent to the scheduler core. And this scheduler core sends invoker module. So invoker module have several different API module to contact with different API of the quantum backend server. So in case of IBM, so we have because the IBM system and the supercomputer Fugaku is installed next to each other, so we have a direct access REST API between IBM and our schedulers. So in case of Quantanium, so they provide a REST API goes through the virtual local area network connected between Fugaku and their backends. So and this is posted to the quantum computer, and the result is registered to database manager to then send to the user. So but in case of IBM actually, so they ask us to use S3 server to exchange the data between user and the quantum computer. So that our scheduler retrieves the data result from S3 server and then get back to the user. So this shows our quantum software stack. So for the user API, we provide something C API, which maybe can be used with traditional HPC programming models such as MPI and openP. As well, so in the middleware layer, we support the Qiskit and ticket and Kudaku to submit it not directly to the Quantum Cloud API service, but our lightweighted scheduler by using our client library. So then users of Qiskit and ticket and Kudaku can also use our mechanism or the Quantum HPC with our lightweighted scheduler and use the Quantanium, Raymay, or IBM Kobe with direct access server connected within a local area network or virtual local area network. So and for the transpilation by IBM, so recently IBM do not allow to submit not transpiled circuit, so that we have some mechanism to get the information to transpile it locally. So users transpile it by themselves by using the Qiskit libraries, and in future we will support several add-on developed by research purpose, or maybe developed by IBM Qiskit C++ team. So authorization is also important. So basically, we expect that our user is a user of supercomputer. But because actually the number of users of supercomputer Fugaku is very larger than a user of quantum computer. So it means that only a part of users can use quantum computer. So we have to check that that users request. This request is coming from the users who have an account of quantum computer or not. So we use token and TLS client certification to send the token data on a secure session of TLS sessions. So our client library automatically retrieves the JWT token gated by user and send it to our QC request server. Then our QC request server identifies and authorizes the user. So unlike general cloud service of quantum commercial quantum service. So there's no user authorization between quantum backend server and users. It means that the quantum vendor do not have to know which user uses their machine. So this is the same. I will omit it. And this is our workflow diagram, so developed by Soratochi-san in our researchers in our unit. So the basic idea is that there is a algorithm of the dependency between jobs. And so there's a server also dedicated to run the workflow. So this server submits job scheduler of quantum computer or HPC scheduler, and some of the job script is running on managed by workflow manager and generated automatically and submitted to supercomputer, and the result is given here. Same in case of the quantum task, same as the HPC task, job script is generated automatically and submitted to quantum computer, and the result is retrieved here. So this is a very simple example of our C and C++ program API. So maybe most of these kind of the API is almost the same in case of the difference is just it is C or C++. In our case, we support C library, because even if you are using C++, you can use C library. So it's more it covers more larger number of users, as well as that we can wrap it very easily for the Fortran, and many HPC users in Japan is still using Fortran, so that but Fortran user can use this kind of the C++ library very easily by using a Fortran wrapper. Will be developed by University of Tokyo. So, and we also support the QSKIT version. So far, this is a bit different from the original QSKIT programming model, but we will try to move it closer and closer to the QSKIT one. So, for example, so far we ask user to explicitly get the information of transpiration and transpired by themselves. But in future, this will be same as the general QSKIT API. So this is a system configuration. So we have an IDP server for the JWT token identification. So we have a front-end and workflow server connected to the Fugaku's job scheduler. So we have several kind of queues in Fugaku's job scheduler because we give a very high priority of the job request to quantum computer from supercomputer. It means that if there are several users try to use the same quantum computer simultaneously, this mechanism will not work. So to control the number of users who can use HPC and quantum with high priority, we use a special queue and limits the number of programs to use quantum computer. So this diagram shows a physical and network configuration quantum HPC in weekend. So I must show it before faster. But anyway, so there is in between in the Fugaku computed node is connected to a gateway called the Fugaku Direct Connection Service Gateway. So this is connected to our request scheduler of IBM and Quantium. So between the Quantium machine is installed in the main campus of Rikan, while supercomputer Fugaku is Kobe. So there may be 100 miles between them. So that we put a virtual local area network to connect it directly. So I will briefly explain so current our HPC quantum applications. So we have several applications, but especially focus on quantum chemistry and machine learning. So in quantum chemistry, actually, we already have a very good application examples developed by Rikan and IBM team and Rikan and the Quantium team. The first one is a ground state energy calculation of the sample-based quantum diagonalization. The second one is a biomolecular chemical reactions push HPC hybrid computing workflow. The first one uses IBM and tightly example of the tightly coupled programming, which is a direct access API and diagonalization by large number of nodes in Fugaku. The second one is a relatively loosely coupled programming controlled by workflow tool. Actually, Quantum also provide a workflow tool to make use of Quantum HPC job scheduler effectively. And we are still finding and doing several applications. So by conducting the test user program. So we call for application proposal to utilize a hybrid platform to research and development quantum HPC hybrid application and get a feedback on our hybrid platform. So and we accept 21 proposal with a very large area of applications such as materials and natural science and design and so on. So at the end, I have to show the schedule, our schedule. So we are almost here, end of the fiscal year of the 2025. So we will end the trial operation and start full operation from next April. But before that, we have a kind of evaluation. So if our evaluation we get a good result of this evaluation, then we can continue from 26, 27, 28, and so on. So that's the end of my presentation. So I will be happy to take some questions.
Thank you, Marco. Any questions? I have a few, but always for others. Okay, I'll start. So in the if you go back to the slide that talks about your C++ front end, I wasn't clear exactly, like when you say you support, say, Q2Q, how does that work with the C++ front end that you guys developed?
Actually, so our program is basically for the C API. So, but we simply say that C API can be used from C++. On the other hand, C++ API cannot be used from C.
Right. But in case of Q2Q, did you write like a backend for Q2Q to support?
Yes. So in case of Q2Q, so first user can construct their circuit by using Q2Q API, and then dump QASM or IR. And this QASM or IR is directly sent to our scheduler.
Right. Okay. So it replaces Q2Q, or Qiskit replaces the C API.
Yeah. So interoperability is not in the level of API, but in the level of the middleware.
Yeah. Got it. Kevin, you go ahead.
Yes, thank you very much. A question, actually, if you go back a slide or two, where you are showing the workflow between the two levels of scheduler, where there is the database and there is the API that is causing the dispatch of the job to the quantum processor. Yes. So what I am trying to understand here is how the dependencies are represented, because some of these blocks of classical code are going to be run based on the results of the previous one. If I take a variational algorithm, this would be the classic case of this. So I have an interleaving of quantum operations and classical operations. How is that dependency represented? How is that synchronized? I did not follow that.
So this QC request scheduler is corresponding to this one, right top one. So the dependency is basically written in HPC program level. So it means that if a quantum circuit request is sent to the scheduler, so in charge of user, the dependency is already resolved.
But it is when the classical code so this is basically being pushed by the classical code. That push causes the allocation of the classical request, and nothing else is going to happen. And then what is it that will allow? Okay, I think I see. Fine, fine. It's a stop and wait at that moment.
Basically, user construct quantum algorithm or load cousin by themselves on this some of the API. And this one, SQC QC run, submit the job to the quantum circuit. So it means that if the result of QC run is requested to the following algorithm, then user have to write wait by themselves.
Okay, so that would be a separate task each phase would be a new task?
Yes.
Okay, thank you. And then, excuse me, I had some problems connecting, so I missed the very beginning of your talk. I am very sorry. Will it be possible for us to get access to these slides to think about after?
Yes.
Very good, thank you.
So maybe I will send the PDF to Ami, then you can distribute it. Is it okay?
Yeah, thank you.
Thank you.
That'll be great. Yeah. I do have a follow-up question. And like if you go back to the C++ sample code that you had, or sorry, not the C sample code that you had, like SQC run call. I'm just
Yeah.
slide, yeah.
Yes, this one.
Yeah, right there. Yeah. The SQC run here, do you specify the number of shots that you want to run, or is each like SQC
yes,
run one
so
shot?
you have to specify this as an
Oh, it's
option
right there. Okay,
of the runtime right
perfect.
here.
Okay, yeah. Okay. Go ahead. Carolina, go ahead.
Is that me?
Yeah.
Yeah, okay. Did you face any challenges or learnings that others of us can learn from in the process of setting this up? I'm assuming there were like back and forth decisions or challenges. Maybe some of them are still there. Anything that can like help us as a community build upon these, challenges instead of having to all go through the same process?
No, I cannot understand your question. Could you repeat?
Sure. So you right now have a really, complete architecture. You have examples, you have codes, you've made some decisions.
Mhm.
In the process, were there specific learnings? So, I mean, part of the openQSE, I guess, is to, put down a framework that can help us all guide, how we're going to build our hybrid architectures. So is there any like specific learning or challenge that you can point out, something that maybe was not obvious at the beginning and you had to make a decision that, either worked or is still a challenge?
Actually, we are still in test and test stages. So, but so far, so for example, so we are providing the training program for our test user program. And so, so we will open our source code after it is completed. So it is still in the kind of the development and beta version. But we will open all the source code, including our schedulers. And so.
Okay, so it's not open source yet, but it will be in the future?
Yes. Yeah.
Okay, perfect.
Yeah, the beta or alpha version is opened, but so if we will keep continue to update.
Sorry, can you repeat that last phrase?
The alpha version is available on our GitHub, and we keep continue to update.
Okay. Yeah, if you can share the GitHub, that would be great. Thanks.
Following up, I have a question on the schedulers that you had. You were talking about when you prioritize, so you prioritize tasks, quantum tasks coming from the supercomputer because you don't want the supercomputer to wait too long, right? So you have some scheduler that prioritizes the tasks. It looks, I guess, as some metadata figures out if this metadata is coming from like an HPC program or if it's coming directly, like it's being scheduled directly. Now, is that second level schedule that you guys have, is that part is that responsible for only one specific quantum computer? So you have an instance
Yes.
of the scheduler for each quantum computer, not one that manages all of them?
So we have one scheduler for one quantum computer.
Okay. And how does the user select? So when they want to select one of those, like the IBM or the Quantinuum one, do they explicitly say, or do they explicitly reserve it? Like you,
So
how,
so
like
so
I missed
far
the
we ask
reservation part.
user to explicitly say what kind of quantum computer they will use. So for example, in this case, IBM Direct Access.
Okay, but do you guys require the user to reserve it as part of the HPC reservation? Like when they use Slurm to reserve their HPC allocation, do they also select a quantum computer at that point, or do they do it on the fly?
So when a user submit a job, so user may select the queue of the HPC site first. So for example, if a user would like to use Quantinuum and supercomputer Fugaku, then when you submit a job with a job scheduler of supercomputer Fugaku, you have to specify Q Quantinuum S or Q Quantinuum M or Q Quantinuum L. So then only these Q are allowed to access our request servers from us, the MPI or other HPC program running on.
Okay, so you essentially require the user to, like, ahead of time select, like at the very beginning when they allocate their job, they select
so
quantum
far,
algorithm.
yes, because we have two very defined type of quantum computers. So 156 superconductive type and 20 qubit ion trapped one. So it means that it means that it is difficult to run the same algorithm, different quantum computer, I expect. And in future, if we have, for example, different type of superconductive quantum computers, IBM or Rikan or others, then maybe it may be interesting to introduce auto selectors developed by Munich.
Okay, yeah, makes sense. I have other questions, but I'll open it up to the floor if anybody has anything else. Okay, I'll ask my last question. You guys worked on, I can't remember the exact paper, but you had this proof of concept of running, showing an advantage of overlapping HPC and quantum operations. So I'm guessing that falls into your HPC QC category that you showed a while back. Can you talk a little bit about that? Like how long is the wait times of running a specific circuit in that model?
Yeah, that is a good question. So, based on our observation, you may also know that each of single shot takes relatively longer time in air-trapped type machines. So on the other hand, it will very fast in superconductive type. But if the number of shots becomes very large, so even with superconductive type, it may take some 10 minutes or something. So that so far, we ask user to identify how long you need, and if the waiting time are so even if we prioritize something, the execution time itself is very long, then it does not make sense. No more. So that we ask users to consider by their service to use which level of programming you will use.
And did you have any data on like how big the circuit is, like how long a circuit takes depending on how the size of the circuit? Do you have any data on that?
Actually, so we made our backend server has some kind of data, but we have not summarized or checked it.
Okay. So I'm trying to just, okay, so how do you, like in the example where you actually did a proof of concept of the SQD, I think, algorithm, and you ran both HPC and quantum at the same time and you overlapped the calculations, did you find that the HPC was idling, or like did you like find an average of how long the HPC would wait for the quantum operation to complete? Yeah.
Actually, so this is a very well-designed algorithm which uses two populations of the algorithm. So if first population using quantum computer, then the other one uses supercomputer. If the second population uses quantum computer, then the other one will use quantum computer and so on. So first we measure the execution time of quantum circuit time and adjust the number of nodes to speed up or maybe so if we use more nodes, then we can speed up the execution of HPC. So that we adjust the number of time of we adjust the number of nodes of supercomputer to use it iteratively and avoid the waiting time of the quantum and HPC.
Okay, so it's specifically designed to minimize the HPC wait times.
Yeah, yes, and increase throughput between them, both of them. Actually, so this figure is very ideal one, and in fact, this is real execution time of the different QPU, and so sometimes we may have a kind of idling time because of the unexpected longer execution time of CPU side.
Oh, on the QPU farm, like
Yeah. So this
was-
white one is QPU's idling time.
Okay.
So this
So
is
there was no idling time on the
this
HPC?
worked very well for the small number, small size of program. But after that, we have execution time of CPU longer than we expected, so that we have a bit waiting time in the QPU side.
And did you try this algorithm in both IBM and the Continuum, or just
No,
IBM?
this is only IBM because this require a large number of qubits, which is unavailable quantum.
Great. Thank you. That was good. Thanks. Anybody else has any questions? I can go on. Technical question, and that'll be the last one. You used RPC. You're saying you use RPC to send, I guess, the circuit and the data back and forth between the HPC and quantum. Did you like write your own RPC, or are you using like gRPC or? So
originally we used our own RPC in our proof of concept experiment, but after that we moved to gRPC. Actually, the performance is not so different, but so if I say that we use our own RPC, or if we say we use gRPC, maybe many users prefer more popular one. So that's why we decided to use the RPC.
So I have a question there, and maybe it's just my ignorance. gRPC here, does it support the different? Well, I guess in this case, you're always sending over Ethernet. But like, let's say in the future, you put a different network interface on the quantum side, like InfiniBand or Slingshot or whatever. Does gRPC support like different interface types or?
So actually, I'm not sure. So communication between client and broker. So we always use gRPC. So on the other hand, communication between quantum backend and scheduler, we use a different protocol or different RPC algorithm provided by this quantum commercial quantum vendor. Because in case of IBM, so they do not like RPC but REST API. So that we have REST API modules to make use of IBM system, even in direct access. So in case of Quantum, they provide gRPC access, so that we use the gRPC between scheduler and quantum backend server. So the basic idea is that we can load several different dynamic library module for different quantum vendor, so to make use of different one in the same schedule. So in some sense, this scheduler may hide different API of quantum vendor by users, because user can use only single method to access the request scheduler, and the difference between the quantum vendors will be hidden by users by RSP.
Okay, help me understand that the QC request scheduler is running on one of your HPC nodes?
No, we have a special node for this.
Okay.
QC request scheduler is between the quantum server and a Fugak direct service gateway.
Any other questions? Go ahead, Kevin.
Just a very minor one. If you go back a few more slides, and this is, again, not important to the core of what you were talking about, but I just had this, I was wondering about it. There, you have these histograms showing where time is going with the two different dispatch and execution models. The most obvious thing on that slide was the Python library time goes away, which is always nice to see. But yes, those. And so what I found interesting is if this is to the same scale, and it seems to be, I found it very interesting that not only does the Python overhead essentially go away, but in the circuit execution times improved somewhat, some more than others, and the polling and transpile time changed radically. And I was wondering if you know a reason why, for example, in case number one, the polling and transpilation time goes up so dramatically from the one model to the other.
So actually, this experiment use Rikan's quantum machine, and their backend server, the polling interval of their backend server is 10 seconds. So it means that if you are lucky and this 10 interval is coming just after the arrival of your request, then polling time is very short. So on the other hand, if it arrives just after the polling interval of the quantum backend server, then it must wait the next polling timing of 10 seconds after.
Okay,
just you are lucky or unlucky.
Okay, just now, please forgive this. This is as a critique, but it is then very misleading to show those dark blue numbers because they are samples where it is known that the variance is very large. Yeah. And so some kind of range and median indication would be much, much better than an anecdotal sample because it leads to unreasonable conclusions. Thank you.
Yes. Yeah, that's correct. But in some cases, in some sense, this is a good example because most of the cloud quantum service are the same thing.
I did have a question about the Qiskit-C API. I thought that you said you started doing some Qiskit using the Qiskit-C API.
Yes, but not yet. We are planning to move to the Qiskit C and C++ Qiskit in future, but so far we are using traditional Qiskit.
Okay. Thank you. Any other questions?